We have two types of BJT, vapor junction transistor, that are NPN transistor, where P type of semiconductor material is sandwiched between two N type of semiconductors. Then the respective terminals are emitter base collector. While at the same time, we can also fabricate the same device as a PNP configuration, where N-type semiconductor material is sandwiched between two P-type semiconductor materials. Okay? And yeah, of course, in NPN type of BJT, the current flows from this collector to emitter. Okay? The current is flowing from the collector to emitter. So this arrow indicates the flow of current, and this is the symbol of NPN transistor. In case of PNP, right, the current is going to flow from emitter to collector. So in the symbol of PNP transistor, right, the arrow is moving inwards to the base from emitter. Okay, this is how we have to remember the symbols. As we know, the BJT is considered of what the PN junctions, right? PN junctions. So definitely there is PN junction diode form within this device. So if we try to model that device in terms of PN junction diode, so we will get the equivalent circuit in terms of diode like this. Okay. So one of the terminal uh, when cat collector, uh, right? Here for NPN transistor, right? For NPN transistor, right? Okay. This this is the cathode representing the collector, right? And this is the cathode representing the emitter. While base is what P-type material, so yeah, this triangular portion represent the P material as well. And E is what cathode, so PN junction is formed between base and emitter, while PN junction is formed between base and collector, right? So in order to turn these junctions on, that is base emitter junction and base collector, or emitter base or collector base junction, as those are diodes, right? We need to apply that barrier potential along these diodes, right? So barrier potential for this particular PN junction diode is 0.7 volt that we have studied in unit number 1, right? So in order to turn on this NPN diode, we have to supply 0.7 volt to both of the PN junctions, right? Or 0.7 volt plus minus 0.2 volt that we have to, maintain across those junctions or diodes of this BJT transistor, right? Yeah. In case of PNP transistor, we can say that the base is N, N type, right? So base is going to form the cathode, while emitter and collector, which are P type materials, so these are going to form cathodes. Okay, so the direction of the diode is going to reverse compared to, yeah, NPN transistor. Both are diodes, so it is both PN and NPN both are going to have the same barrier potential of 0.7 volt, right? So we have to apply the 0.7 volt plus minus 2 voltage in case to turn on those devices. So this is the physics that we have to remember for a particular BJT, right? Suppose in case of NPN transistor, right? Okay, so along those junction, right? Along the junction, that is this emitter base and collector base junction, right? as these are the PN junctions. So of course, along this junction, we are going to have the depletion region. So yeah, this depletion region will look like this, right? In P type material, of course, along those P type material, along this junction, we are going to have those negatively charged electrons, concentrated or accumulated along this region, right? And while in N region of the emitter and collector both, of course, there is going to have the positive holes accumulated along the junction, right? And this will form depletion regions. Okay. Now, as we to conduct or to overcome this depletion region, we have to apply the threshold voltage of 0.7 volt along this, and according to that, we have to turn those junction on and off, right? And means what we are doing, we are going to apply certain potential across those junctions, and how we are going to do that? That Yeah, we are going to apply certain voltage between this base emitter and the base collector, right? So if we have to turn this emitter and base junction forward bias, right? We have to apply certain voltage, and according to that, uh, whatever the voltage we are required, right? We call this applying of voltages to this device, applying proper voltages to device, so that this device is controlled in on motion or off mode, right? On mode or off mode, right? So applying such required amount of voltage is called the biasing, right? It's called the biasing. And when this device is unbiased, means no voltage is applied along the terminals, no potential or no current is flowing through these terminals. When no potential is applied, no voltage applied along these terminals, means what? It is unbiased. And when it is unbiased, the scenario or the physics within this device will be look like this. Okay. Yeah, in order to work out, we have to turn on or control the device, we have to apply certain voltages, or we have to do biasing. Okay. So of course we have to apply certain modes, right? Okay. So we have three regions where we get these regions by applying certain voltage. Across, as we know, these are what the junction, PN junction. So of course PN junction is going to have a forward bias and a reverse bias mode, right? So based on the different modes, right, whatever the modes we have, right? So suppose this PN junction, right, this emitter and base junction is suppose forward bias, and this junction, collector and base is junction, is a reverse bias. So this junction is going to be have very high resistance, and this junction is going to have very low resistance. So we will have a path from emitter to collector like that. From where we will move in a path from emitter to collector having low resistance to high resistance, like. So this is what the transition of resistance, and we call this as transistor, right? And suppose both the junction, right? Suppose this emitter base junction is reverse bias, so a very high resistance, and if collector and base junction is also in reverse bias mode, right? So this junction will be in reverse bias mode. So this both the junction will yeah, provide, or this both junction will offer a very high resistance and no current will flow. So the device will be off. So likewise, according to the what are the condition or the biasing or the modes, this junction or the junction are going to operate, this BJT is going to have the different regions of operation. So cut-off region, when the base emitter junction and the collector base junction, right, both are reverse bias. So device is off or cut off. So this is called the a cutoff region of the operation of this transistor, and we can say that the transistor is switch off, right? And suppose the both emitter base and the collector base junction are forward bias, right? If the both junction are forward bias, so depletion layer is vanished, right? The very less resistance is there, very minor resistance. So maximum current will flow through this device. So when both the junction are forward bias, maximum current is going to flow. So we call this region as saturation region, and the transistor, we say that the transistor is on. So in saturation region, transistor is fully on, and maximum current is going to flow. Okay. Now, Another mode we can have is that one of the junction is forward bias and one of the junction is reverse bias, right? So with this junction, emitter to base is forward bias, so there is very less uh, resistance, and collector to base region or junction is what, reverse bias. Okay, so forward bias and reverse bias. So we will get two different resistance, right? As we discussed. So this mode is called active region, right? Inactive region. And so in this region, we use this device and amplifier, right? So in cutoff and saturation region, we use this device and switch, right? Whether it is going to off or on. And in the active region, we use this device as an amplifier.